Welcome to this Academy TV. In this video, we're gonna focus on electric potential due to a single point charge. Before we solve some questions here, let's consider electric potential when distance is given. The formula for electric potential when distance is given can be expressed as VB minus VA is equal to KQ into 1 over arrow A minus 1 over arrow B. This is the formula here. So let's derive the above formula for more clarity. Using the fundamental formula for electric potential, we say that electric potential V is equal to work done over charge. This is our equation 1. We want to prove this particular formula here. Okay, so we are proving this formula from the fundamental expression for electric potential, and the formula is V equal to W over Q. From equation 1, the parameters can relate. Okay, from equation 1 here, the only parameter that can relate distance here is work done. From this equation here, the only parameters that can relate distance is work done. Please take note. And from the formula for work done here, we say that work done is equal to class force times distance, where the force here at this point is referred to electric force. Please take note of that. Where the force here, since we are treating electricity here, where the force F is equal to K Q, small letter q, over r square. All right, and this is what we have to consider here, that whenever we are given numbers, whenever we are given numbers, we are given force in number, we are given distance in number, and we are asked to calculate work done. This is the expression for work done here. Please take note of this. But whenever the parameters for work done is expressed in variable, if force is expressed in letters or variable, to calculate the work done, whenever the parameters are expressed in variable means letter, the work done here will be work done will be equal to class integral of f of s ds. So if the distance is s, it will be f of s ds. So at this point here, the distance here is r, so we use f of r dr. Please take note. So from the given parameters here, for arrow as distance, for arrow as distance, the expression for work done here will be equal to integral of f of r dr. Please take note of this. So replacing the f of r here for work done, our work done will be equal to integral of k q small letter q over r square dr. So our intention here is to integrate this particular expression here. How do we integrate here? We only integrate here depending on the dependent variable. So the expression here is only depending on r because we are integrating with respect to r here. So anything that does not express r here will be called a constant. Please take note. So k capital letter q small letter q will be a constant. So shifting out the constants to integrate, I will have something like this. I will have w here will be equal to k capital letter q small letter q integral of 1 over r square dr. So the next thing here is to make this expression here to be linear in order to use power law to integrate. Okay, making the expression to be linear, I will have this to be w is equal to kq small letter q integral of r raised to minus 2 dr. So using power rule to integrate this, I will have this to be w will be equal to class kq small letter q. I will plus up this power here by 1 and divide with the new power. I will have this to be class r raised of minus 2 plus 1 over minus 2 plus 1. Please take note of this. So this will be equal to class kq calculate small letter q into r raised of minus 1 over minus 1. So class, everything here is going to be w will be equal to minus k q small letter q r raised to minus 1. Our intention here to simplify this, to evaluate this here, I will make this power here to be positive. Making the power to be positive here, w will be equal to class minus kq small letter q times 1 over r. Whenever we are taking any expression from numerator to denominator, the sign of the power will change. So to make this power here to be positive, I will take this from numerator to denominator. So our total expression here will be equal to class minus kq small letter q over r. So this will give us the work done. But we are not asked to calculate the work done. Of course, if you are asked to calculate electric work done, this is our electric work done in case. Okay, if you're asked to calculate electric work done here, the formula for electric work done is minus k q small letter q over r. So please pay much attention to this. This is the formula for electric work done. We can call this equation here equation 2. Now I replace the equation 2 into equation 1. When you replace equation 2 into equation 1 here, when you replace equation 2 into equation 1 here, we will have something like this class. V is equal to minus k q small letter q over r over q. Let's simplify this here. When you simplify this here, we have v to be equal to class minus k q small letter q over r here divide by q over 1. If you apply bulk mass, our V will be equal to minus kq small letter q over r times 1 over q. This will cancel this. I'll be left with minus kq over r. Please take note. So this is our electric potential, but not electric potential difference. So let's express the electric potential difference at this point. To express electric potential difference, we have to take 2 points, A and B. So taking 2 points, A and B, the first point here will be for V at point A, I will have the expression to be VA to be equal to minus KQ over RA. Now for electric potential at point B, our VB will be equal to class minus KQ over RB. So to express the difference in electric potential, we give us electric potential difference. To express the difference in electric potential, we give us electric potential difference. Please take note. So the difference here will be VB minus VA, which is equal to, let's replace. We have to replace VB. VB is replacing this here. Our VB is minus KQ over RB minus, that is this minus here. Please don't forget. Into our VA is minus KQ over RA. Okay, let's simplify this here, class. This will be equal to minus KQ over RB plus KQ over RA. Taking the items here, that is evaluating this here. If I have something like this minus 2, if I have something like this minus 2 plus 3, this is the same thing as plus 3 minus 2. Please take note of this. So applying this concept here, I will have this to be VB minus VA to be equal to KQ over RA minus KQ over RB. So let's take items here. Let's factorize here. When you factorize, we have VB minus VA will be equal to KQ into 1 over RA minus 1 over RB. This is the formula for potential difference when distance is given. So let's solve some questions here to apply this formula. Question 1, please. Let's solve this question here. They said, consider a point A which is 85 cm north of a point charge minus 45 times 10⁻³ coulomb, and a point B which is 60 cm west of the charge. Determine VB minus VA. Let's solve this question here. Solution first. In this question, we are asked to determine the electric potential difference, that is VB minus VA. To calculate electric potential difference when distance is given, we use the formula VB minus VA equal to KB into 1 over RA minus 1 over RB. Please take note. So let's understand this question here clearly. let's understand the equation perfectly before we impute the values. So we have the sketch here, a sketch like this. From the equation, we have north, we have west. Of course, let's complete this part here. We have east and we have a south. So from the question here, they said we should consider a point which is 85 cm at the north part. So at the north part, we have to consider a point here, A, and it is 85 cm. In meter, it is 0.85 in meter. Okay. Now we have to consider a point again, B, at the west. This is west here, B. This is B. This point B, and the distance here given to us here is 60 cm. In meter is 0.6 meters. So again, there's a charge at the point, that is common charge between the west and the north. So this common charge here is here, and we call this Q, and Q is given to us as minus 45 times 10 raised to power of minus 3 coulombs. So we have something like this. We can make this search here. Okay, so we're asked to find VB minus VA. So let's replace the values here. When you replace the values here, we have something like this class. VB minus VA be equal to K is constants, which is 9 times 10 raised to the power of 9 times the charge there is given to us from the sketch, or from the equation, is given to us as minus 45 times 10 raised to the power of minus 3, okay, into 1 over the distance, that is arrow A, is given to us as 0.85 minus 1 over the distance at the point of B is given to us as 0.6. Please don't forget, when you punch your calculator here, I will have this to be minus 405 times 10 raised to the power of 6 into, so when you punch your calculator, 1 divided by 0.85 will give us 1.1765 minus 1 divided by 0.6 will give us 1.6667. 1, 2, 3, 4. Okay, now let's punch our calculator here to get the final answer. VB minus VA will be equal to class minus 405 times 10 raised to the power of 6 into minus 0.4902. So our last answer here is 1 point, that is 198.531 times 10 raised to the power of 6. So finally here, to convert everything here from here to standard form, I will have this to be class 1.9853 times 10 raised to the power of 2 times 10 raised to the power of 6. So finally, I will have this to be 2 times, approximately 2 times 10 raised to the power of 8 in volts. Okay, so our answer here is 2 times 10 raised to the power of 8 in volts, approximately. So all you have to do to get more video on electric potential and potential difference is to hit the subscribe button.